Hey everyone, in this video I'm going to show you how to calculate the theoretical top speed of a car. I'll be doing this for a Bugatti Veyron Super Sport, mainly because there's a lot of information about the technical specifications of that car online. The steps that we'll be using are first showing you the equation that we're going to be using, then we'll do a unit check to make sure that the sides of the equation, both sides, make sense in terms of the units that we'll be using, and then we'll go over the knowns, which are the technical specifications of the car, and the assumptions that go along with those knowns that we're using, and then we'll get to the solution. The first thing we need to do is define power. So power is defined as the rate at which work is done. Whenever you hear the word rate, you should think of something per unit time, which is why we can write it as the work done per unit time. And if I define work as a force acting over a distance, so force F acting through a distance d, then on the denominator we can put in t for time, and you can see that this d over t, that's a distance per unit time, that's the same as a velocity. And so we can write that the power is the same as force times a velocity. Now we know that our engine is producing a certain amount of power, and the question is, what is that power being used for? So we can write this expression here where I'm saying the power of the engine is being used to overcome some amount of aerodynamic drag, and it's being used to accelerate the vehicle. And so let's split these two terms up into their own individual terms. And so first we'll look at the power to overcome the aerodynamic drag. From here we have the force times the velocity, so we can break this power up into a force of aerodynamic drag times the velocity that we're currently driving at. The expression for the aerodynamic drag force is given by this expression, which I'll explain these terms in the next whiteboard. So we have 1/2 rho v squared CdA times the velocity, and you'll end up noting that in this term there's actually a velocity cubed because we'll have the v squared times v. The power for acceleration can be given by this expression, again using this FV. So we have the force for acceleration times the velocity that we're currently driving at, and the force for acceleration we can break it up into the well-known F is equal to ma, so we'll substitute in ma here times the velocity. And when we're driving at our top speed, that means we are no longer accelerating. So the A in this case, because we're trying to find the top speed of this car, is going to be 0 meters per second squared. So you'll note that in this equation up here, the P acceleration term here drops out because it's equal to 0. So we end up having that all of the engine power at our top speed is only being used to overcome the aerodynamic drag. So here's our final equation that we'll use to solve for the top speed of our car. The power of the engine is equal to 1/2 rho v cubed CdA. The v cubed comes from the multiplication of the v squared and the v term from the previous whiteboard. Rho is the air density in kilograms per meter cubed, so the air that we're driving through. V is the velocity of our car, which is what we're solving for, and that's going to be in meters per second, so we'll need to convert that to kilometers per hour, miles per hour when we're done with this. CD is the drag coefficient, and it's unitless. And A is some characteristic area, which for cars is going to be the frontal area in meters squared. And just a side note, the way that CD, the drag coefficients, are determined is by measuring a drag force on your car and then dividing by 1/2 rho v squared times some characteristic area, and everyone's agreed that the characteristic area is going to be the frontal area. If you're talking about airplanes, if you're talking about like a wing, then the characteristic area is not the frontal area of the wing, it ends up being the wing area itself. Let's do a quick unit check to make sure that both sides of our equation have consistent units. I'm going to work from the left first, so just power. We said that's work over time. Work has units of joules, time has units of seconds, and joules per seconds gives us watts. Now, if we do the other side, we have the 1/2 rho v cubed CdA. Rho has the dimensions kilogram per meter cubed. Velocity cubed, a velocity is just meters per second, so a velocity cubed is going to be meters cubed per second cubed. CD is unitless, and then area has units of meters squared. So you can see that the meters cubed and the meters cubed, those cancel, and we are left with kilogram meter squared per second cubed, and that's what I'm showing here. What we can do then is note, because we need to get from here to make sure that it's the same as watts. So if you look at the base units of joules, then you can see that it's kilogram meter squared per second squared. This is just something that if you're unsure of, you can just look it up on Wikipedia or on Google. And so the base units of joules are kilogram meter squared per second squared. If you look at this, it's kilogram meter squared per second cubed, which means we can break this up into kilogram meter squared per second squared, and we have one extra per second left over, so we'll put that here. This is joules. So that's the J here, and this is per second, so that's the S here. Joules per second is equal to watt, and that means that both sides check out in terms of our units. Now, what if you didn't know the base units of joules, or you couldn't look it up for some reason? Let's look at power from the definition that we had, force times velocity, and force you can write as ma. So if you look at m, you know that mass is in kilograms. Acceleration, you should be able to think of like the acceleration from gravity, 9.81 meters per second squared. That has units of meters per second squared. Velocity is meters per second. You multiply this through, you get kilogram meters squared per second cubed, and you can check to make sure that that checks out with this one, which then matches, which you know is power, so it matches with the power up here. So there's a few different ways to check the units in this equation, but we've made sure that they're all consistent in our case. Now let's move on to our knowns and our assumptions. I'm going to be doing this for a Bugatti Veyron Super Sport. As I mentioned before, I'm taking these values offline. I'll post the links in the description to where I found these values, but it was just after a quick perusal of some different websites. Took the best ones I saw. Power of the engine is given as 1200 horsepower at 6400 RPM. This doesn't matter in our analysis, but that's just what it was given as. And the assumption is that this is at the wheels. So this is the power delivered at the wheels, and it's an assumption that I'm making here. The width of the car is given as 1998 millimeters, which is just 1.998 meters. The height is 1190 millimeters, or 1.190 meters. And if you multiply the two together, you get the frontal area of 2.378 meters squared. The drag coefficient is given as a range of values from 0.35 to 0.70, depending on the configuration of the car. And we're going to use an assumption of 0.36 because this is on the lower end of the drag coefficient where we're trying to reach the top speed. You would assume that the top speed would be reached at the lower of the drag coefficients. The density of air we're assuming is 1.225 kilograms per meter cubed. This is a standard air assumption. And a big thing, kind of big, is that I'm neglecting rolling resistance. I'll add that in to another video. I'm going to do another analysis with rolling resistance added in, but we're going to neglect it for this particular example, and we can move on to the solution. Great, so let's plug in those values that we had on the previous whiteboard and solve for velocity. However, first thing you need to do is that we are given the engine power and horsepower, and you'll note from our unit check that horsepower is not the same as watts. We need to convert to watts. So the first thing you need to do is take the 1200 horsepower, use a conversion factor of 745.7 watts per horsepower, multiply the two together, and you get the engine power of 894,840 watts. This is the equation that we're using. P engine is 1/2 rho v cubed CDA. Plug in the engine power here, and then plug in the density here. V cubed is what we're solving for, or V is what we're solving for. CD of 0.36 and a frontal area of 2.378 meters squared. All we have to do now is solve for V. So we move everything to the other side, take a cube root, and find V, and we get that the velocity, top speed, is 434 kilometers per hour, or converted to miles per hour is 269.7 miles per hour. And if you check this, compare this against the Wikipedia page, it ends up saying that it's 431 kilometers per hour for the top speed. So it looks like it's pretty close. Other websites or guides will tell you that there's a slightly different top speed, but this is a very general first shot at finding a theoretical top speed for any particular car. This just happened to be for the Bugatti Veyron, but you could use this for any car. But just remember that we're neglecting rolling resistance. So if we add in rolling resistance, the top speed will decrease. But that is for another video. So if you stayed this long, thanks for watching.